multistage probabilities. And we'll start off pretty simple with the multistage probability. So multistage means more than one thing is happening at once or in sequence. And let's take 2 coins. Let's say those 2 coins are a quarter and a penny. And we flip both coins. What's the sample space look like here? So let's suppose I always say what the quarter did first and the penny did second. So the possible things that can happen is the quarter could have a head and the penny could have a head too. The quarter could have a head while the penny could have a tail. Now, those are the only 2 ways a quarter could have a head. The penny has 2 options. And then other options are the quarter could have a tail and the penny could have a head, or the quarter could have a tail and the penny could have a tail. So I'm pretty sure that there are 4 different outcomes. Sometimes we put them in parentheses when they're paired together like this. So this could be my sample space. Each thing that happens is really a pair of things, right? Because I have multiple things going on at once. Now, are these equally likely? Well, my belief is that the quarter is a fair coin, right? This idea of fairness. So that means the head or the tail is equally likely for the quarter, and the head or the tail is equally likely for the penny. So altogether, they should be equally likely. Since there are 1, 2, 3, 4 of them, each of their probabilities should be 1/4. That seem reasonable? We can illustrate this in a lot of different ways, and a couple of those are, aside from making the list the way I did there, is to make a table to approach this. And so let's say I write information about my quarter in columns and the penny in rows. And the quarter could have a head or a tail, and the penny could have a head or a tail. And then inside of the table, listing quarter first, so I have to have some way to do that, I could have a head, quarter, head, penny. I could have a tail head, listing the quarter first. I could have a head tail down here, again listing the quarter first, or I could have a tail, which are these outcomes I had here, but organized in a table. Each there is kind of messy, a little better. So if you have only 2 things you're comparing, a table is nice. Just a note here, table is good for 2 things. A tree diagram is another thing we use sometimes, and a tree can be used for more than 2 things, which we'll look at in a moment. So I have the quarter go first, and the quarter could be a head or a tail. And then branching off from the quarter, we look to see what happens for the penny. And from that head, a penny could get a head, or the penny could have had a tail. From the quarter's tail, the penny could have had a head, or the penny could have a tail. And then to complete the sample space, we just flow through the tree. So following that top line of branches there, one outcome is head, head. Flowing through the next branch would be, again, starting at the beginning through like that, and I have a head, tail. And then I can flow through the bottom part of the tree, tail, head, and then finally tail, tail. It's kind of what I was thinking when I was drawing this out up here at the top. So typically when we're trying to find the outcomes in some kind of multi-stage probability where there's more than one thing happening, a table or a tree is helpful. Table, you can only do two things at once. Tree, you can keep extending the tree, and if you're not careful, though, it gets pretty messy. So sometimes other techniques are employed. But this is all we have to worry about for now. But no matter how I do this, I get there's 4 outcomes, and I'm assuming they're equally likely because the original events were equally likely there. Okay, not too bad. We could have more than 2 things happen. So we could have 3 coins. So maybe we have a quarter, a penny, and then a dime. And again, you can't really make a table because if I make a table has rows and columns. And if I put quarter here and penny here, then there's nowhere for dime to go easily. There's a way to kind of fake it, but not do that. So we're going to make a tree here. And so we'll just flow through these in a tree. And it doesn't matter whether we flip them one at a time or we flip them at the same time. This will list out the outcomes. So quarter first, and the quarter could be a head or a tail. And then the penny gets to go next. And so from this head, the penny could be a head, or the penny could be a tail. And then down here, it could be a head, or it could be a tail. And then the dime gets to go last. And so a dime has a head or a tail. So from each of these, we have 2 more branches. So head, tail, head, tail, head, tail, and head. That's not very good, head. Better, and tail. And to find the list of complete outcomes, besides just looking at the tree, you just kind of flow through the tree to list them. So at the top, I have head, head, head. And then head, head, tail would be another. And so it's just carefully moving through the tree. And people have wrote computer programs to do that. And I'm kind of done with this top row up to the penny, so I have to jump down to the penny's tail. Head, tail, head. And often what I do when I'm making these trees, I'll kind of draw out from each of these to make sure I don't miss anything. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. So I have 1, 2, 3, 4, 5, 6, 7, 8 outcomes. And this kind of came up, or did come up in math 211. There are 2 choices for the quarter to do something, times 2 choices for the penny to do something, times 2 choices for the dime to do something. And we have a bunch of choices in a row. Multiplication of those tells us the total number of choices at the end, which is the total number of possibilities of outcomes here. A couple of ways to think about how much each of these outcomes is worth probabilistically. So we could just naively assume that each of these are equally likely. So this would be 1 out of 8, and that would be 1 out of 8, and so on. And that's a reasonable assumption here, since I'm assuming each quarter, penny, and dime here are fair. Another way to think about that is to actually write the probabilities on each branch. So the probability of getting a head from the quarter, that was 1/2. The probability of getting a tail from the quarter was 1/2. And if these are all fair coins, then every branch here has a probability of 1/2. I'm going to go label those probabilities on every single branch here. And you may ask, well, why are you doing that, Gary? It's a lot of 1/2s. Well, although the quarter and penny and dime are equally likely, not all situations are equally likely. This idea of writing the probabilities on the branches allows me to use a tree in situations where each outcome isn't equally likely. once I have the probabilities on the branches, if I flow through any one, like make believe not make believe, but let's actually look at this one right here. If I trace it back through the tree, multiplication of the probabilities of the branches associated with that outcome would be its probability. So if I take 1/2 times 1/2 times 1/2, that would be 1 times 1 times 1 over 2 times 2 times 2. Notice I get the 1/8 that I thought I would get if these were equally likely, because there's 1, 2, 3, 4, 5, 6, 7, 8 different outcomes. Now, again, we have to really think through each situation. Are the outcomes of each simple event equally likely? Sometimes they are, sometimes they're not. In this case, they are. So those are my different outcomes. And I can answer all kinds of questions like that. Like maybe somebody might ask, what's the probability of flipping the 3 coins and getting 2 heads and 1 tail? Now, I'm not really specifying order there. I'm just saying, hey, I want 2 heads and 1 tail. So I would just look up here to try and figure out, okay, when are there 2 heads and 1 tail? Well, here's 2 heads and 1 tail. Here's 2 heads and 1 tail. Here are 2 heads and 1 tail. I see 3 different ways it could happen. So favorable outcomes there would be 3 out of total 8. So once we have a tree, we can answer pretty much any question somebody asks about the situation of flipping a quarter, a penny, and a dime. All right, let's try another example. Let's suppose we roll 2 6-sided dice. And then I want to sum the dice numbers. So keep in mind about the dice. So each die has the number 1 through 6 on it, right? So for 1 die, my sample space is a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So for the sum of 2, well, if they both got the lowest number, the lowest sum we would get is 2. If they both got the highest number, the highest I would get is a 12. So I think the sample space for the sum of 2 dice would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible outcomes when I roll 2 dice and I add up the values that I see. All right, question. Are these outcomes equally likely? Am I just as likely to get a 2 as I am a 6 or a 12? So if they're equally likely, the probability of getting a sum of 2 would be the same, question mark, as the probability of getting a sum of 3, and so on. What do you think? Do we need to do more work to figure this out? Not the same likelihood, said Jimmy, and I agree. We got to do more work than this. So we could do one of 2 things. We can make a tree for this. What does the first dice do? Well, the first dice, if we made a tree, so we could call them like die number 1 and die number 2. It could be my white one and my green one. So let's say I roll the white one. I can roll them at the same time. It doesn't really matter. And then I look at the green one. the white could be a 1 through 6, right? We roll, either I get a 1, or I get a 2, or I get a 3, or I get a 4, or I get a 5, or I get a 6. And then from this 1, what could the green do? Well, the green could do anything it wants. The green could be a 1 or a 2 or a 3 or 4 or 5 or a 6. My tree's getting a little messy here. The white had 6 possibilities. The green has 6 possibilities. So altogether, there should be 6 times 6, which is 36 possibilities. And I only have 11 outcomes. So some of these outcomes are going to be more likely than another, because 11 doesn't go into 36 for sure. The tree, I don't really have enough space to make it here, so I'm going to do this a little different. I'm going to make a table. And I'm going to put the green ones in the top. So I could get a 1, or I could get a 2, or I could get a 3, or I could get a 4. I can make tables neater than I can trees, but try way harder to make a neat tree, or a 6. And then the white one on this side, well, it has the same possibilities, and then we put them all together. I'm going to run out of room here. 1, 2, 3, 4. Ooh, just barely enough room if I squeeze that in there. And so inside here, I'm going to write the possible sums, right? 1 plus 1 is 2, 2 plus 1 is 3, 4, 5, 6, and 7. 2 plus 1 is 3, 2 plus 2 is 4, 5, 6, 7, 8. 3 plus 1 is 4, 3 plus 2 is 5, 6, 7, 8, 9. It's kind of a pretty pattern, isn't it? 5, 6, 7, 8, 9, 10. Let's see, where am I at? 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, and a 12. And so what I can see here is the sum of a 2 only occurs one way, right? 1 plus 1. 12 only occurs one place, 6 plus 6. But getting a 6, man, there's 1, 2, 3, or sorry, getting a 7, excuse me. There's 1, 2, 3, 4, 5, 6 different ways that can happen. So if we re-summarize this table in another table where we have the sum versus its probability, we've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are all my sums. And then the probabilities are, how many are there total here? 6 by 6 is 36. So getting a 2 is 1 out of 36. Getting a 3, that's 2 out of 36. Getting a 4 would be 3 out of 36. 5 would be 4 out of 36. 6 would be 5 out of 36. And I know this can be reduced, but let's not worry about that. 7 is 6 out of 36, and then it starts dropping again. 8 is 5 out of 36. Let's double check. 1, 2, 3, 4, 5. 9 is 4 out of 36. 10 is 3 out of 36. 11 is 2 out of 36. And 12 is 1 out of 36. Probability is easy in some regard. It's just the ratio of favorable outcomes to total outcomes. Measuring that is a challenge, and counting them all up can be a challenge too. So probabilities, somebody could easily ask me a probability question that could take me days to figure out the answer to, just because of the complexity that happens pretty quick. Now here we only have 2 things happening at once, right? 3 things can happen. Anybody ever play a card game where you have 5 cards in your hand like poker? Those are super hard to count because there's so many things that can happen with 52 cards and 5 cards at a time, and multiple people having 5 cards at a time. So these very, very quickly Crazy stuff has to happen. Question, if I were to add up all of these probabilities here in my probability column, can anyone tell me what they're going to add up to? There are 36 possible outcomes, but I'm talking about adding all of these fractions. 1 over 36 plus 2 over 36 plus 3 over 36.
Sorry, I didn't hear that part.
Yeah, I want to add up all the probabilities. What are they going to add up to, do you think? Can anything else happen besides what I've shown here? This should be everything that can happen. And if everything can happen, that would be 100% of what's going on. So anytime you make a situation like this and you list all of the individual probabilities, whenever you add them up, it has to add up to 1. If it doesn't, something went wrong. Right? So these are all my different outcomes, right? These are all the different sums I can have. And these are their probabilities. All the probabilities should add up to 1. Some other things to just think about here. The probability of getting a sum of 6 is not a simple event. Simple means you can't break it down, and getting a sum of 6 I can break down, because a 6 could be a 5 plus a 1, or it could be a 2 plus a 4, or it could be a 3 plus 3, it could be a 1 plus 4, or it could be a 1 plus 5. So there are 5 different ways that 6 could have happened. So this probability of getting a sum of 6 is not simple. If I ask, what's the probability of getting a 1 on the white die and a 5 on the green die? Well, there's only one way that could happen. So that right there is simple. That's the only way that can happen. A 1 on the white and a 5 on the green. But getting a sum of 6 is not simple. It's made up of all these other events. Is getting a sum of a 12 simple? The answer, yeah, that one's simple because there's only one way that can happen. So this one is a simple event. All right. Let's see. I think we're almost ready to take a look at the next activity. I just need to talk about 2 more things. At the end of section 8.1, they talk about simulations. And a simulation means you're finding a way to do the experiment without actually doing the real experiment. So for example, let's say that when I shoot a basket, it's either going to go in or not, but I don't have a way to shoot a basket, so I'm just going to flip a coin to simulate putting it in the basket. So it's when I do something else, it's a make-believe situation. When we do a simulation, that simulation has to have random selection involved. And the big problem there is, what does random mean? And that's a tough one, because often in our normal lives, we use random in a different way than it's meant in math. So I was talking to my sister the other day, and she said, yeah, you know, I went to this random bar down the street and I met this guy. And I'm like, well, there was really nothing random about that bar, Tracy, because it was right down the street from your house, right? And you've been there before. And the guy wasn't all that random either, because he went to the bar too. So we often misuse the word random. So when I flip a coin, that's supposedly random because it's spinning in the air. I can't really predict how many times it's going to spin, and then it lands in my hand somehow, or it bounces off the table. So random in some sense has some unpredictability to it. So the weather is pretty random, but it's guided by all these forces around it. So there's a lot of different things that push around that idea. So examples of randomness are flipping a coin, if we're not that magician, rolling a die. Picking a card from a well-shuffled deck. But being truly random is a really hard thing to do. Like I mentioned, I knew a guy that could pretty much almost all the time, he could flip that coin just right and he could tell you what it was going to be. Now rolling a die, I don't know too many people that can roll a die in such a way on a surface that it's always going to land the way that they want. But the coin thing I've seen happen an uncanny amount of times. And then there's all kinds of card tricks. So aside from card tricks, if it's a well-shuffled deck, you can randomly pick a card from there. But in computers, we try to make these random number generators. And that is super, super hard to do. And I just want to demonstrate that spreadsheets have a random number generator. So let me get a new tab here. Blow it up a bit. So I'm going to show a couple of different random number generators between. So if you want to make something happen, you can insert a function or formula, and there's all kinds of different ones you can put in there. If you happen to know the name of them, then that's even better. You just go equals and start typing. So I start typing RAND, and it said, hey, okay, I know rand array, and I know rand between. Rand creates a random number between 0 inclusive and 1 exclusive. That means you could get 0, but you won't get 1. And it has as many decimals as the computer has available to it. So if I just do rand parentheses, nothing in the parentheses and hit enter, it'll give me a random number. And I can't remember how many decimal places the computer has to deal with. And notice it keeps changing the random number because I mentioned before, whenever you do a random number generator on a computer, every time something changes on the sheet, it regenerates that randomness. And eventually it's going to run out of places. Okay, it's starting to run out of places, I think. Let's just type something here. Yeah, okay, so I have 3 more places than it can handle. So let's back off a little. Oh, I'm in the wrong spot. Okay, so that's as many digits as it has there, but every time I do something else, it's going to regenerate, and I'm going to get a slightly different random number. And notice it's always a proper decimal. It's somewhere between 0 and 1. It is possible to get all zeros, okay? But that's one out of many possibilities. It's going to be extremely unlikely. This random number generator, let's copy that. Put that in my, yeah, there we go. I can put that in here. Just want to talk about this random number generator for a sec. Make that bigger, please. All right. So the spreadsheet is set to only have certain number of places it keeps track of. So let's see, how many do we have? We've got 2, 4, 6, 8, 10, 12, 14. There are 15 places here in this random number. Each place here could be a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? So I have 10 digits. So I have 15 places with 10 digits each. So thinking back to when I was counting the number of possibilities for the 2 dice. There were 2 dice, they each had 6 possibilities. 6 times 6 is 36. With the coins here, there were 3 coins, each had 2 possibilities. 2 times 2 times 2 is 8. So in this particular spreadsheet random number generator, there are 15 places. Each place has one of 10 digits each. So that would be 10 choices here, 10 choices there, 10 choices there. That's 10 times 10 times 10, 15 tens. There are 10 to the 15th different possibilities, right? Let's list that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what's that? Thousands, millions, billions, trillions. What's after trillion? Quadrillion. There's 1 quadrillion different possible numbers the spreadsheet can throw at me here. Getting all zeros there is 1 out of that many, right? You have a way better chance of being struck by lightning than you do of having the computer give you all zeros for that random number. Now, a true random number generator would really have infinitely many possibilities to choose from. And the other problem is here, this is a program created by a human, and humans really aren't that good at being random no matter how hard they try, right? If I ask you to pick a random digit, you got to think about it for a second. Oh, what's a digit again? Oh yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I'll pick 9, then 7, then 2. It turns out if you had a human just generate a whole bunch of digits and say they did it randomly, we would find patterns to it, that it wasn't really truly random. All right, so, but we use computers to do simulations all the time. About 10 years ago now, there's a program called Microsoft Excel. Some of you may have used it before. It was around before Google Sheets was around. And it is a spreadsheet, and it has a random number generator in it too. Let's see, how do I get a new one? And so just like the one I was using, blow it up a bit, I could use the rand feature, which is equal rand, close the parentheses, don't put anything inside, and you get a random number. And again, there's a whole bunch of digits I have to work with there. Let's do it. It's wrong way. And eventually it's going to run out of digits. Yeah, notice it gives me a bunch of zeros. So it's probably about the same as Excel. Do they use exactly the same code to generate the random number? Probably not, but there's a lot of common code people use in these things. Well, about 10 years ago, it was discovered that the Excel random number generator was more likely to give you a number less than 0.5 than it was greater than 0.5. And Microsoft put a lot of time and money into fixing that so it more equally distributed those numbers, so it was a more uniform randomness. Because people use these random numbers to do all kinds of simulations for reality, and so this was messing up people's work in those simulations by being biased toward lower numbers than higher numbers. Point, being random is hard. We're not that good at it, but we're getting better at it. But nature is really good at being random, and so we try to learn from nature. All right, so when I was creating these simulations here and these random samples here, I was using the random number generators to do so. So just a quick example of how I did that, and then we'll play with the second activity. So there's another function called rand between. And rand between, instead of having this wild decimal there, just works with whole numbers. So I would like a random number between 1 and 3. So you give it the high number, you give it the low number, and every time you run it, it just gives you a new number there. So like, let's see, F4 did not, oh, F4 does work on this one now. Why is it working here? So every time I hit F4 on my keyboard, it's going to regenerate a random number. You can see this random's changing all the time. This one only has 3 choices. So sometimes it gives me a 2 again. But I'm either going to get a 1 or a 2 or a 3. And the theory of this function right here is if I did this a million times, I would expect to see just as many 1s as 2s as 3s. If that's a good random number generator for the rand between. So when I had tried to make the random spinner here, I have a hidden row in between 3 and 5, and that picks randomly 1, 2, or 3, and then it kind of looks at my spinner numbers and says, okay, if you got a 1, show me a 1, but if I do it again, If it's a 2, show me a 5, and if it's a 3, show me a 9. And here, this would be a 1, 2, or 3 for 2, 6, or 7. So it turns out you can manipulate these random number generators to do almost anything that you want. And that's kind of a thing that's used a lot when people run simulations of reality. So instead of actually doing, now why would I do that? Well, the answer why is it was a lot of work for our class to generate these numbers right here. And so what do we have here? Let's see, I got a couple, I have 2 header rows. So I have 60 spinner against spinner trials there. And I have 100, is that right, over here. So I have 160 altogether. So we had to work pretty hard altogether to get 160 random number generations. Whereas if I can do it with a spreadsheet, then I can make that spreadsheet do a whole bunch at once. And to do that, again, all I have to do is come up with a way to generate a random number. Let's see, where was I doing that? Over here. So here's my random number between 1 and 3, and then based on that, it picks a spinner number over here. And once I do that, I can do that all day long. So I could easily take this last row and fill it down and randomly generate spins as many rows as this thing will give me. I think this will give me 1,000 at first, and then I can ask for more. Why am I doing this, you might ask? Good question. Okay, so here's a whole bunch of spinner information. I'm trying to look at the idea of the law of large numbers. Remember, what does the law of large numbers tell us? The law of large numbers connects theoretical probability to experimental probability. I want to look at that one more time. So we do a large enough set of trials of an experiment. Maybe it's 1,000, maybe it's a million. The experimental probabilities will be close to theoretical probabilities. Often, right, we have theoretical probabilities, but often we don't, like the shooting the free throw thing or the weather. And there's just a ton of other situations out there. It turns out that the theoretical probabilities are kind of rare. And in reality, if we want to know a probability, we have to experiment to find it. And the more trials you do, the better information you have about what's actually happening there. And so that's what I was trying to get at here. So in this case, I just did about 1,000 counts here of spinner A and about 1,000 runs of spinner B. Now, instead of actually spinning it 1,000 times, which would be a painful exercise, I had the computer use its random number generator to generate 1s, 5s, and 9s and 2s, 6s, and 4s. And what I should expect to happen is if each of these is just as likely to occur, the 1, the 5, or a 9, that they should each occur 1/3 of the time. 1/3 as a percentage would be about 33.33%. And you can see that one of them is pretty close. And I have about 1,000 trials going on here. The first few rows here, remember, are other stuff. So it's not actually 1,004 rows, but they're close. And then if I reshuffle, can't do it. Oh, come on, you can do it. I guess I have to just do something else on the screen. It recalculates everything, and notice I have a slightly different set of probabilities. So I just told it to look below and count how many ones divide by the total number of numbers, count how many fives divide by the total number of numbers below, and so on. And notice that they're around 33% on average for these guys here and here. And every time I tweak my spreadsheet, it regenerates them and I get a slightly different set of results. Now, the theoretical probability here in my spinner, so let's look at spinner A. So A had a 1, a 5, or a 9. So theoretically, the probability of getting a 1 should be 1/3. Now, experimentally, we'll look at this a couple of different ways. The probability of getting a 1. Actually, we'd rather get a 9, right? That's the bigger one. Let's do the 9 because that makes us happy because then we win if we have the 9. If we look back at some data, if I look at my almost 1,000 spins here, a 9 came up 33.57%. So I did 1,000 experiments using the random number generator. From the class data, if we look at column A here, and then in this is for a few of us. I think there were 60. Oh, no, we got more. Keep going, how many were there? There were 100 spins there. So if I just count the 9s, and then say only count it if it's a 9. From the class data, there were 32 9s. There's 100 spins there, so that would be 32 out of 100. So we get a couple of different answers from the experimental. From the class data, we got 32 out of 100, a little under 1/3. When I looked at my simulation of it, I've done it a few times now. What was the last one? The last one was 34.67. Before there was a 31 or a 32 there. So let's go with the 34.67. Here, there were 100 trials. Here, there were about 1,000 trials. So that would be like 3, 4, 7 out of 1,000, say. So what does it mean to be large enough? Well, it turns out millions or billions sometimes. We got 100, we got 1,000. We're kind of close to 1/3. So we're just kind of playing around with this law of large numbers. So there's two things I want to look at in the next activity. And so let's switch to the multi-stage probability activity. I want to look at two questions. Come on. In the big picture and a few questions in the smaller picture. Same 3 spinners we were working with before. At the top and then down below, I link to the spreadsheet that has the class data. So first thing I want to do is experimentally looking at the class data. Does A have an advantage over B or B over A? Does A have an advantage over C, or is it C has an advantage over A? So these are the 3 comparisons we can make: A versus B, A versus C, or B versus C. So based on the class data, what can we tell? Is A better than B? Is A better than C? Is B better than C, or vice versa? Based on those right there, we want to say, okay, can we make a strategy if you get to choose second? So for example, when I sat down with Amy, I said, okay, you can pick first. And she picked spinner B. She had a reason for doing that. And I said, okay, I'm going to pick spinner C. And I picked spinner C for 2 reasons. One, I thought a lot of people would pick spinner A because it's the first one and it has a 9. And then looking at her spinner, I saw that 8 is bigger than all 3 of her numbers. So I said, okay, C is the last one and it's got an 8. That looks like a good one. So is it possible to, if somebody picks spinner B, that you can then say A or C is going to do better, or if somebody picks spinner C, you know that A or B is going to do better? Can you come up with a strategy based on the data from those up there? Then what we want to do, instead of looking at the class data, we want to think about this in terms of making a table to figure this out. And so what I mean by that is not a table like the class data, but a table like the green die versus white die. This was 6 on 6. Here I have a table, or is it, of heads and tails for the quarter versus the penny. And another example where I can make a table like you're going to make here. Do you ever play rock, paper, scissors? I'm sure most of you have. Paper, scissors. That if I was playing against somebody else, so me versus you, right? I could either throw rock, paper, or scissors, and you could throw rock, paper, or scissors. And then there's 9 different things that can happen here. So I want you to do something similar for spinner A versus spinner B versus spinner C. So I'm going to split you up into groups to do that. And then what we want to know is like who's the winner, right? So rock versus rock, tie. Paper versus paper, tie. But the spinners, nobody ties. Paper versus rock. Let's see, paper covers rock, right? So that's a me. Rock crushes scissors, so that would be a you. Rock versus paper, let's see, paper covers rock, that would be you. So I can go through this and figure out what's going on. Is rock, paper, scissors really fair? Paper versus scissors, scissors, that's me. Scissors versus rock, that would be you. Scissors versus paper, let's see, that would be, did I do something wrong here? Scissors versus, oh, rock crushes scissors, that one would be me. And this one would be you. So you can see I have 3 ways to win, you have 3 ways to win, and there's 3 ways to tie. So this game is fair. Are spinner A versus B fair, or B versus C? All right, let's do this. And then once we do this theoretically, we want to ask ourselves, okay, do we want to revisit our strategy from the experimental one? And then what if we played all 3 spinners at once? Will one win more than the other 2? That's the last question to figure out here. So group time. All right, so here we are. Let's see where we're at. So let's see, A versus B, who won more from our class data? Anybody figure that one out?
Was it B?
I think B won more. I think it was like 60 to 40, something like that. Okay, what about A versus C? That was a theoretical one.
A.
A won more there. And how about B versus C? I have silence.
Our group chose B, but I'm not really sure. That one was kind of confusing.
I thought it was a tie when I looked at the data. So we didn't have a lot. What did we have there for the class data?
It was like 30-30.
B versus
Yeah.
C. Yeah, it was
Yep.
30-30. So based on the class data, it doesn't, like, they're equal based on the class data. So that's all we have to go with. So we're just going to say this is a tie. All right. So strategy, right? So you're the second person to pick. So Amy comes along and she says, I'm going to pick spinner B, right? I think that's what you picked the other day. So she picks spinner B. Is there a spinner I would pick if she picks spinner B? Let's see, what beats spinner B? Well, if she picks B and I pick A, she's going to beat me most of the time. So it looks like the best I could do is hope for a tie. So I would probably pick spinner C. So somebody else comes along and they see that 9, they say, I'm picking spinner A because it's got the 9. Okay, so you're gonna play me, I just picked spinner A, what are you gonna pick?
C.
Because A beats C, yeah, you're gonna pick C. And then if somebody picks spinner, let's see, C, what would you pick? I pick spinner C, you get a choice of A or B, what would you pick?
Would it be A?
It would be A because we have evidence that A beats C more often. Yeah, so this would be the strategy. This is the first pick. You make the second pick. So based on our class data, this would be the strategy right here. Oops, strategy. All right, so we're about out of time, but I just want to
For the
set up.
second, would we choose C?
What's that?
For the second, would we choose C? If they chose A, would we get C?
They chose
Didn't C
A.
get beaten by A?
Let's see, do we do that right? They chose A. Oh, no, C would get beat. So if somebody chooses A, we would
choose
want to
B.
pick B. Oh, wait. Oh, yeah, B beats A. We would want to choose B there. Thank you. You're correct. So first person chooses A. We have a choice. B beats A, so we would pick B so that we could win. Yeah, so we want to win. All right, so win. A wins here. And B versus C, so far our data shows a tie. We need more information. More trials probably, or maybe it is a tie. So the second idea was to look at it theoretically. So let's pick B versus C since that one ended up in a tie. So B, so we're going to make a table. So this is the theoretical part. Theoretical. And I got to get the options down. I can't remember what the numbers are. It's on this page. All right, so B is 2, 6, or 7. So B, 2, 6, 7, and C is 3, 4, 8. How many possible outcomes are there with these two spinners? There's 3 times 3, there's 9 possible outcomes, right? So C gets a 3, B gets a 2. So I'm just going to put the winner in the box. C is the winner, agreed? If C gets a 3 and B gets a 6, B is the winner. 3 versus 7, B is the winner. So theoretically, we can make a prediction about what's going to happen. If C gets a 4 and B gets a 2, C is the winner. B, 6 versus 4, B is the winner. 7 versus 4, B is the winner. But down here, C gets an 8. Who cares what B gets? C always wins. So based on this theoretical table, which spinner would you want?
B.
C.
Oh, we get 2 different answers. B and C. How many C's are there? 1, 2, 3, 4, 5. So the probability that C beats B is 5 out of 9. The probability, according to this theoretical table, that B beats C is 4 out of 9. I don't know, I see the chat flashing. Did I make a mistake? Let's see. 8 beats 6. Let's see, what am I missing here? 8 beats all of those, right? Do I have this right? C wins all the way across. C beats 2, otherwise 6 and 7 win. Yeah, that looks correct. So it looks like C wins more often when, on average, when C beats B. This is the theoretical data. So if we did that experiment more, we would expect to see C winning more times because C had that 8. So that was my guess before I was looking at C. That 8 is pretty powerful. So we can make one like this for C versus B. We can do another one for A versus B. And we can make another, what are we missing? A versus C. And this will theoretically tell us which one is more likely to win. And then we can revise our strategy based on that. So if I come back, let's see, C does better. So let's go back here. So now we have a little more information. We can see C does better. So let's see, if somebody picks spinner B, I would definitely pick C. If somebody picks spinner C, I would definitely pick A. Okay, so I made a good guess here about the tie because C is going to do better. Strategy. Yeah, so it turns out the same strategy, once you got over that tie there with more information, this strategy is still a good one. And again, the strategy is for how do you pick a second spinner? Is there a way so that you're going to be slightly better off? And it turns out there is, regardless of which person the first pinner. So playing this game, I would rather have somebody else pick first. I would say, yeah, you pick first. And they'd be like, yeah, I'm picking spinner 9. Spinner A with a 9. I would say, oh, good, I'm picking spinner B because I have more chances to beat you.
Now I know why you had me pick first.
Actually, I haven't done this in a year, so I totally forgot who beat what.
I'm just teasing.
I was just